What up, guys? So in this section, 11.2, system of equations and of systems of linear equations in three variables. So how is this really any different from the last section? Well, essentially, all we've done here is just added another variable. We're going to call it z. And so when you have a system of three variables, to be able to solve it, you need three different equations. So I'm just going to write down what our equations are for this problem. Okay, so what's the idea behind doing this? Well, when we had two variables, we were talking about we have essentially two equations of a line, and how do these lines intersect, right? And we said they could intersect at one point like that. They could never intersect if the lines were parallel, or they could intersect infinitely if it was the same line twice. And you'll have to excuse my attempt at overlapping lines. And so now that we have three variables, what are these talking about? Well, they're talking about planes. So think of kind of like pieces of paper. It's essentially what a line is in 3 dimensions. So something like this. So this should kind of in your head look like three paper pieces of paper floating above each other. And so the planes are going to grow like lines in every direction. So that way, that way, that way, and that way. And you can tell that because these are directly like almost stacked on top of each other, these lines, or these planes, excuse me, they will never intersect. So this is equivalent to the parallel lines. Okay? And so just like the lines, there are the same types of solutions. Here, we have no solution. You have one solution. So where three planes, and this is very difficult for me to draw. The book actually has a lot of good pictures in there, so I would suggest that you look there for good pictures. But essentially what you're having is three planes that intersect, and like I said, terrible pictures, but they only intersect at a single point, right? And this is the case of two lines that only intersect at a single point. And the final thing is they intersect at infinitely many points, right? And what does that look like for lines? Well, the only way that can happen for lines is if it's the same line twice, but this is not necessarily true for planes because they have another dimension. So assume we have one plane going like left to right, so this is kind of think of them like crossing at an X, right? So this plane in the middle here is what they share. And think of another plane kind of orthogonal to you, so sideways, so you could barely even see the piece of paper, cutting right through them. Well, the the plane that these two shared, right, is kind of like a plane, but since this one only cuts straight through it, right, it only intersects at a line, but a line still has infinitely many points. So even though our planes are three-dimensional, even if they only intersect at a line, it's infinitely many points. And likewise, you could still do the same thing where you say, oh, I have the same plane 3 times. The answer to this is also infinitely many points. In a strange sort of way, a plane doesn't really have any more points than a line does. I mean, you kind of know it does because a plane is made up of infinitely many lines, but you kind of get the idea. Okay, so that's the logic behind what we're doing. We're just essentially working in 3 dimensions now. At how many different points do planes intersect? And what's interesting is that no matter how many dimensions you go up to, whether you're in 2 dimensions with lines, 3 dimensions with planes, 4 dimensions, 5 dimensions, your solutions are always only ever going to be one point they intersect at, infinitely many points they intersect at, or no points they intersect at. They're never going to intersect at something like 2 or 3 points. It's just not possible. Okay, so now how do we solve these guys? Well, you can use either of the methods that we learned in the last section, which is substitution or elimination. But what I would recommend for most of us, it's just a little cleaner to do elimination. So once I get past two variables, I prefer elimination to substitution. And so what we're going to do here is, it's the same kind of idea. Why did we do elimination or substitution? The idea is to get an equation that only consists of one variable, right? And once we do that, then we plug it back into our original equation which only had two variables. And so then we just had a value for both x and y, and we were done. We're going to do the same thing here, but it's just going to take a few more steps. But the same kind of intuition here. We want to eliminate a variable. Since I see x and negative x here already have the same number, opposite sign, I'm going to eliminate my x's. So I'm going to add a and b together to come up with a new equation. And so x plus negative x, that's 0x. The x's go away. Negative 2y plus 3y, that's just y. And 3z plus negative z is 2z, right? And then 9 plus negative 6, well, that's positive 3. And so I will do it here once again, just for those that are visual learners. Right, so this is equation A, this is equation B, and when I add them, when I add them together, I'm going to get equation A plus B. Okay, and so this becomes 0x, this becomes y, this becomes negative 2z, positive 2z, excuse me, and positive 3. So you can see that our equations match. That's cool. And so now what we're going to do is we're going to do that one more time, except we would need to combine two other equations together. And so you could do A and C or B and C. I'm going to choose to do A and C. Actually, I'll do B and C because B already has a negative. So what I'm going to do is multiply 2 times B. Okay. And what is that equation going to look like? Well, 2 times B is, got to write B here, what the equation looks like. And when I multiply these, I get negative 2x plus 6y minus 2z is equal to negative 12. Right, and so now I have 2b, and I'm going to add it to c. And the resulting equation is going to be 2p plus c. You don't really have to label these that way. I just do it to kind of keep track of what I'm doing. And so c is 2x minus 5y plus 5z is equal to 17. And so when I add these together, what do I get? The x's cancel, which is what we want because we got rid of the x's in the first equation. We want to do the same here. 6y minus 5y is y. Negative 2z plus 5z, that's positive 3z. Negative 12 plus 17 is 5. And so now we have another equation of two variables, right? So let's scroll back up here, and I'm just going to write b plus c, even though I did multiply b by something. It's y plus 3z is equal to 5. And now this should look very familiar to you because this is essentially what we did last section. Two variables, two equations, and we need one of them to cancel out. So I'm going to multiply b plus c times negative 1, so I have a negative y and a positive y, and I can cancel these out. So I'm going to copy this really quickly. Let's scroll down. Paste it here. Cool. Okay, so negative 1 times y plus 2z equals 3. That's going to give me negative y minus 2z equals negative 3. And add it to my second equation of just y's and z's. And what does this give me? Well, the y's cancel out. Cool. Negative 2z plus 3z is z. And negative 3 plus 5 is 2. So z is equal to 2. That's great. Now to figure out y, what do? Well, we just plug it into our variable of two equations. So y plus 3z is equal to 5, but we know z is 2. So we can replace the z with 2. and that tells us y plus 6 is equal to 5. Subtract 6 from both sides, and that tells us y is equal to -1. So now we have y and z, and how do we find x? Well, we go all the way back to where we started, to the 3 original equations, choose any of these. I'm just going to choose the top one for no particular reason. Scroll down, paste this here. Oh, looks like we lost the y for some reason. I'm just going to check to see. X minus 2y plus 3z equals 9. Cool. And so now we know what y is. We know y is -1 and z is 2, so we can replace both of the variables. So we'll go x minus 2 times -1 plus 3 times z, which is 2. Write that again so it doesn't look like a z. And multiply x plus 2 plus 6 is equal to 9. We subtract, we can combine these two. X plus 8 is equal to 9. Subtract 8 on both sides, and that gives us x is equal to 1. So the solution for this problem is the ordered triplet, because essentially we're working in 3 dimensions. And so x is equal to 1, y is equal to -1, and z is equal to 2. And this is the point which all 3 of these planes, right, these planes intersect. So they just intersect at one point. Cool. I'll see you in the next video.